Hello, James Sykes, CEO, President, Director of Baselode Energy Corp. We released some excellent news on Monday, March 7th, and I'm here to update with a little bit more details on those news results. And been getting a lot of requests about understanding radioactivity, so we're going to address that here, and hopefully people can understand down the road. Just flip past the forward-looking statement right into what we're going to talk about. We announced 25,000 counts per second, CPS. What does that really mean? Well, it's high levels of radioactivity, and that's always what we're looking for in the uranium space. So we are very excited about that. Hole AK22-11 is by far the best hole that we have intersected radioactivity on, and we will get into that again. Uranium mineralization is still open, 150 meters long strike, very exciting. And we just keep finding more elevated radioactivity as we continue to the south and southeast. And the structural model there suggests that as we continue going in that direction, the structure should be getting better. And there is unconformity potential to the east, at least we believe so. We'll get into that too. What is radioactivity? Basically alpha, beta, gamma fission decay products from uranium and other elements. But we know that we've got uranium here, so we're focusing on that. And fission is basically when the uranium atom splits apart into two new atoms, and that split releases energy. And that's the whole process behind nuclear energy, really. So it's a very simple concept. The more uranium we have present in our rocks, the more radioactivity we will have. And we measure this radioactivity using handheld scintilometers and downhole gamma probes. And then we send all of the assays off to the lab for confirmation of U308 results. But I'm going to point out that not all scintilometers or probes are created equally. Therefore, you can get different CPS readings from the same type of rock. And it really has to do with the crystal sizes of either your handheld scintilometer or your gamma probe. So you can imagine that you've got a piece of rock and you stick a scintilometer with a large crystal, let's say the size of a baseball. That's going to get a lot of radiation compared to a crystal size that would be the size of a raisin, which would get a little bit of radiation. So your CPS between those two crystal sizes would be much higher for the larger volume crystal versus the smaller crystal. But what we do here at Baselode is we will be standardizing everything internally on our own. We will use an RS-125 scintilometer, handheld scintilometer, for reporting our radioactivity results. And we also do use a triple gamma probe for downhole. We don't release those results typically, they're for internal purposes only, but in this presentation we will look at some of that. You cannot compare our results to other companies. It's just unfortunate that everybody seems to report in different standards. Some companies will only release results that are X amount of meters greater than this radioactivity level. Some companies will report X amount of meters with a maximum radioactivity level and a lower and a cutoff radioactivity level. What we are doing is we're trying to summarize everything, what we see in the intervals that we believe will have the right uranium results that we would put out a news release. We're trying to do the same thing as we would do with assays, and that we are providing composite summaries. So where everything is basically a weighted average composite when we put out those average CPS results. We do use a cutoff CPS of 300. So anything above 300 will be included, and anything below 300 counts per second will be excluded, with the exception that we do allow for 2 meters of internal, no greater than 2 meters of consecutive internal dilution. So if I have to get into that later on down the road, then I will, but not in this one. That's what a handheld scintilometer is. That's the one that we use. And that is a 2GHF triple gamma probe. It's 1.8 meters long. So it is a very big tool. Which these are the two types of equipment that we use to measure radioactivity. And that's what we'll be showing here today. And it's very simplistic. You can stick the handheld scint right on the core boxes and get radioactivity levels that way. However, if you do that, especially in a high radioactive environment, you'd get a lot of background radiation from all the rocks around where your scintilometer is. And that would flood the radioactivity results. However, when we get into higher levels of radioactivity, so above that 300 counts per second, we take the rock out of the core, walk away, into a zone with background radiation so that we can get a direct measurement from the core, as you can see being done here, 25,000 counts per second on this piece of core. To better understand the radioactivity results, so we're going to look at the assay results from 3 of the holes from last year in the discovery fence. We released this in a previous presentation, grade thickness calculations, and to simply go over that, what that is, GT, grade thickness. So you're taking the grade of the rock in weight percent U3O8 and you're multiplying it by the thickness, so the interval that we've reported. You can get an example of what you see here, but I want to bring you to the 2 examples below on what 100 GT can mean. So we're not reporting 100 GT. This is just a very simplistic way to show that a GT is just a unitless number, really, and it's a guide, really, but there are multiple ways to get the same type of GT. So in the first example, 10% over 10 meters, you multiply 10 by 10, you get 100. What if you have 1%? 1% over 100 meters, while 1 times 100 is also 100. So you can have lower levels of either radioactivity or concentrations of U3O8, but on the converse side, have a higher width, and then you can get the same GTs. These are the results that we released last year, both from radioactivity results and the corresponding assay results when they came out. But what we've done in this slide right here is now we've gone back to the radioactivity results, and we have calculated the weighted average, the composite weighted average over the exact U3O8 intervals. So you can see that the intervals themselves all match up. And these are the corresponding radioactivity results. Hole 1 had the best RT. So RT is what we're just going to simply call a radioactive thickness, multiplying the counts per second times the width of the interval. In hole 3, you can also see some interesting results there. I'll make mention of this one right away, though. The second interval, the first interval in which we intersected radioactivity within the calc-silicate, is a little bit of a spurious thing going on. And I will explain later on, but we do believe that we shaved something. We just clipped something down there that probably had more radioactivity to it. Still doesn't look like it was very big at all, but when we're seeing the highest levels of radioactivity here, basically 1400 counts per second, you would expect to see a much higher grade than what we're seeing here, which only came back at 0.11. We were scratching our heads, and both Cameron and myself really believe that we had clipped something, and it shows up in the gamma probe too. So that's why we think that there is something else down there, but that leads us to hole 11. And so I've taken these results, but I take away the one in the red box and organize them basically by RT with the corresponding GTs. And so you can see in hole 1, RT of 10,000, we basically get a GT of 2. Cut that in half, and it works for both. Pretty, there's a little bit of differences here and there, but relatively it's almost in half. And then you go down to the next one, and basically you cut those by a third, and it basically works out. And as you get lower in your RT values, you get lower GT values. So it is it's a good way to correspond and to have quick visuals and understanding of, if we calculate our RT, what could your GT be? But again, your GT could be 2% over a meter, could be 0.2% over 10 meters. So just a couple of things that you have to take away from that. But typically, the higher the radioactivity, the higher the percent of U3O8, which brings us to what we released on Monday. Now, that first interval in hole 8, 911 CPS over 6.4 meters is very similar to what we're showing in hole 3 up above. And the RTs are basically the same. A little bit greater meterage is probably what's providing for a larger RT. Hole 9, very similar to hole 1. However, the radioactivity results are much higher than hole 1, and the interval is less. So we can expect a higher grade out of that over a smaller interval. Then we get into hole 11. Now, hole 11, we originally reported as 1583 CPS over 6.5 meters at 201 meters depth. Now, what you see in the red there is a recalculated version of that. that it's 1820 CPS over 7.1 meters. However, that was measured on 2 meters of core because we had 5.1 meters of core loss within that 7.1 meter interval. And that is something that I will explain too, that I think we're even underestimating the potential of radioactivity in that interval based on the downhole gamma probe, which really lights up in that area. Which, looking at the RT, you can see that's basically, until we get to the next level, that is the highest RT that we have. And it's over a short interval with high radioactivity. So we can expect good results from that. And then the next interval where we did have 25,000 counts per second, again, it's a pretty high radioactivity level, about 1,300 counts per second over 12 meters. So both good in radioactivity levels and width. And it gives us our highest RT levels to date, basically 50% higher than what we're seeing in hole 1. So very excited to see what we'll get back from that. But I also note that this is all from one drill hole. We've got 2 intervals with greater than 10,000 RT. So, and they're within 30 meters of each other, actually within 15 meters of each other. This is exciting. This is hole 11. This is going to be great. So as we continue to intersect more radioactivity and release those results along with U3O8 assays, we can do something like this and simply build a background for you, the investors, the viewers, to really get an understanding of our results and provide yourselves with an early indication of what you could be seeing. Again, there is no direct correlation between the radioactivity results that we release and U3O8 grades. They are basically there for guidance purposes and just preliminary guesses. So hole 11, we did have visible uranium, 12,500 CPS over that 10 centimeter piece of core. And that was part of a much larger interval that returned 1.29% over half a meter. So high grade core, that's what we like to see. But what we released on Monday, 25,000 counts per second, so twice as much radioactivity over 0.1 meters. You can still see the uranium. This time it's not black, it's all the yellow and the orange, plus within the red. And you can also see little black nuggets throughout some of the red intervals. That's visible uranium, much more disseminated and spread out throughout a structure. High levels of radioactivity, we can expect good results from that. So we're excited to see what goes on there. And that's the calc silicate. And the calc silicate really built from what we saw in hole 3, in which we did have 2 meters at 0.11% U3O8. This is what the calc silicate looks like. If you've seen a lot of mineralization from the Athabasca, you should know right away that you're looking for red. I don't see red in any of this. The only red I see are the 2 red lines that we've got on there. And so between those 2 red lines is a 2 meter interval that returned 0.11% U3O8. Here it is in a close-up, and you can see that the red arrow is pointing to 2 nodules that we circled, but then there are a couple other ones that we circled as well. Now, I want you to remember this picture, because this explains why I think that we are not seeing the grade that we should see in this interval. I think we really just skimmed something, like just shaved a centimeter off of something. And that when we assayed this, when we split the core with the circled marks are still in the boxes out at site, and the core that went in for the assays did not have the circle mark. So it's disseminated. It's kind of like a nugget effect of mineralization. If you don't know what a nugget effect is, please do your own research. But that's what we think is going on, and the gamma probe, I do believe, shows that. And this is what the mineralization looked like, nodular, compared to what we're seeing in hole 11. Big difference right away is the red. The red is very prevalent. It's very structural. That's what we're seeing. That's what we want to find. We want to find the hematitic oxidized fluid systems along the structures, and that we have uranium associated with it is absolutely brilliant and fantastic. So this is why we keep going south, and it gets better within this calc silicate unit. But even below that intersection in hole 3, there were other smaller intercepts, and within those you can start to see a little bit of red. So there is an indication that these 2 zones between hole 11 and hole 3 should be connected, and the structure should continue on broadening as we go towards 11 and hopefully well beyond there. This is the mineralized zone in hole 11. Right away, your eyes probably popped and saw the red right away. Now there's a contact here as well, indicated by the orange. So metasediments are all on top and the calc-silicate mineralization is down below. But even looking at that calc-silicate mineralization, you can see that there is quite a bit of red in there. And there are a lot of structures and cracks, and this is where we're seeing a lot of elevated radioactivity, quite a bit of it. So we're going to look at the gamma probe and really touching on this whole calc-silicate, but just another way to look at radioactivity and start making comparisons. So the downhole gamma probe, again, basically the same concept as a scintilometer. After we're done drilling, we send the probe down on a wire line, it records the radiation in the rocks around it. So we're not looking at directly at core, we're looking at the hole that was cored and the rocks from whence it came from. And on the top scale is your CPS. I've capped it all at 10,000 CPS, and the left-hand scale is the depth. So from 0 down to 400. Now, I must also note that the levels of radioactivity that are measured in the gamma probe are not going to be the same as are measured with the handheld scintilometer. Why? Because it's that crystal size. There's a little bit of a larger crystal size within this gamma probe than there is in the handheld scintilometer. So we will get more radioactivity from the same intervals. In each of the images that I will show as well, is I will also distinguish the 7,000 counts per second line. There's no real significance to it. It's a visual thing for us to look at as we go through this. And you can see in this first example from hole 1, there's two discrete peaks that are above 7,000 counts per second. There's the interval that assayed 0.13% over 15.5 meters. And you can see the elevated radioactivity associated with it. So it works out nicely. However, what is very curious, and I think this is again one of these nugget effects and shaving type of ideas, is that the highest peak, which is the bottom one, assayed 0.66% over half a meter, whereas the upper peak, in which we had the highest scint values and clearly visible uranium, had 1.3% over half a meter. Regardless, that 7,000 counts break is basically a good point for, or a good cutoff for assuming where you would expect to see high grade, and we're defining high grade as 0.5% U3O8. So let's look at hole 3. Hey, hole 3, there's the gamma profile. Here's our 7,000 counts cutoff. Now you can see two discrete peaks isolated from each other by over 100 meters. This upper zone assayed 0.24% over 5.5 meters, and you can see that the radioactivity is of higher concentrations, but over a much narrower interval. But we're still seeing that 0.67% over half a meter. So we're seeing that high grade above 7,000 counts. It's working. But this one, 0.13% over half a meter. How did that happen? And this is where I think that we honestly shaved something down there. We literally caught it by not even the tail, but by the fur off the tail. And so the gamma probe picked up something larger at depth. Our assays, as I described, is I think that we basically had left where the shaved part was, which is probably about 1 millimeter or about 1 centimeter wide, which had those nuggets, are all in the core boxes and were not incorporated into the assays. Just an unfortunate nugget effect. But I think this does show that there is more uranium mineralization down there than what we have reported. And now let's look at hole 11. Hopefully you can see it right away, but that interval between 200 and 225 meters is it's tight. There's a lot of radioactivity going on there. And that's why we think there's a lot of potential on this. Here's our 7,000 count cutoff, and you can see multiple wider intercepts and peaks, even between 7,000 to even 4,000. There's a lot of peaks going on there. So highly radioactive in this area. Here's the interval with the core loss, 1820 CPS over 7.1 meters, but we had 5 meters of core loss. And then here's the other interval of interest, basically 1,300 CPS over 12 meters, and that includes 25,000 counts per second. Also note that on the right-hand side of the scale, I did cap everything off at 10,000 counts per second, so these peaks do go beyond 10,000 counts per second. So none of the other holes that we have seen have done that so far. And The upper zone of mineralization that we've seen so far seems to be pretty flat lying. We basically just caught the tail end of it in hole 11, and then we've got our calc-silicate mineralization within the broader calc-silicate, and you can see that it does seem to grow as we go to the southeast. And there's also a contact zone of mineralization. Let's look at the core loss. Okay, let's really understand this core loss at the contact. When you've got no core loss at all, you can see your run blocks there should go down in a fashion like that, slightly being offset along the core, or they will go down in a straight line. Each run of core is 1.5 meters in this box, and we drill 3 meters of core per run. And every run you get a block, so 2 10 meters, 2 13 meters, 2 16 meters. When you look up in here though, you don't get that pattern. Right away you can see that there's core loss in there. You go from 195 198, it's a lot of core loss. 198 201, 3 meters, there's no way there's 3 meters in between those blocks. And same with 201 204 204 to 207, there's a lot of core loss in here. So to break it down, you can see the core loss occurring right at the end of the run at 198. Then we've got 2.5 meters of core loss over 3 meters between 198 201. So it's between these green lines next is where we've got our radioactivity. And we've got a lot of core loss. We've got about 5.1 meters of core loss within this interval, and only 2 meters of core to measure the radioactivity. So in the first run from 201 to 204, the core there that we've measured 600 CPS over 0.5 meter of core. In the next interval from 204 to 207, which is the red zone, we're averaging 2,400 counts per second over that 1 meter. That's one of the highest consistent radioactivity levels that we have seen at Accio. And we've got 2 meters of core loss within there. As we continue on that to the first 60 centimeters from 207 to 207.6, there's still core loss there. But as you go from 207.6 down to 208.1, you're still getting 1,900 counts per second over 0.5 meter. So you're getting consistently higher radioactivity within this broader interval of core loss. So if we go to our good old gamma probe within this interval between 190 to 230 meters, let's look at the core loss within these intervals. Here's our 7,000 counts per second cutoff line just for visual purposes. Here's the interval of 1820 over 7.1 meters. So this is, and we only measured 2 meters of core off of this, and the rest is all core loss. But you can see a lot of radioactivity within here. And on the bottom interval where there is no core loss, again, you can see a lot of radioactivity that is just in there for just for visual purposes. But let's go back and focus on the core loss interval. That red zone that had the highest levels of radioactivity is right here between the black lines. And if you see what the gamma probe is doing there, a gamma probe, boom, it's right off the scale. This is why we like this. This is why we think that there is more mineralization than what we discovered, than what we recovered from the drill hole. So very exciting, and we've informed our drillers to be a little bit more, much more efficient in recapturing all of the core, especially when they come into these zones, so that we can have a better control on mineralization instead of going towards the gamma probe. But there's a perfect example of why we use the gamma probe to define mineralization when we can't do it with the core because it's non-existent. I'll also point out this interval up here between 198 to 201 meters. In the handheld Scint, there was no radioactivity being measured. However, we've got 2.5 meters of core loss in here, and you can see the big peak that's happening in there. So we're under the impression that there's far more radioactivity than what we have in the core, and this is a much broader zone. This is basically a 30-meter zone of almost continuous mineralization. This is why we got to keep going south and southeast. And there it is, exploring to the southeast. You can see the trend of mineralization in the upper and the lower zone is going from the northwest to the southeast. The upper zone being the one on the right, the lower zone being in the calc-silicate to the left. Now that we're hitting the contact within the area, radioactivity is picking up, mineralization is picking up, very exciting stuff. Let's expand on this, though, why we really like the Southeast. This is in our corporate presentation. We've been explaining this a lot, and the background image is a EM anomaly, an airborne EM anomaly. It measures about 1,500 meters long by about 500 meters wide. However, I'm going to elaborate on this more now that we do have the airborne magnetic results back as of January, which just shed a lot of light for us because we can see more geology now. So here's the high resolution airborne magnetic survey. You can see a lot of lineaments happening. The yellow dot right in the middle is ACIO. But when you follow everything up here, you follow those red lines in particular, you can make out a fold structure. Now, folds are important in a lot of commodities because this is where you get a lot of structure. You get a lot of structure along the limbs of a fold. You get a lot of structure at the hinge of a fold. And there seems to be a very good correlation between what we're seeing at ACIO and this potential here. So we do think that as we continue to the southeast, our structure should be getting better and better. Looking at that EM anomaly, that's from our corporate presentation, though. So I'll also highlight, if you look to the southeast of that anomaly, you can see that tail. Here, follow the white line, which is basically a rough little axis, but you can see that tail at the southeast end of that white line, indicating that there's still a more conductive anomaly as we go southeast. This is from the same survey, but at a different, I guess, a different resolution, or it's supposed to be at a deeper depth. You can see that anomaly is open to the southeast. That's not closed anomaly, and the tail drags out nicely in that direction. So everything's looking open. Here's that white line again along the axis. Everything's looking open as we go to the southeast. Looking at the mag as well, we'll draw on that white line plus a little bit of extension to get into the hinge of the interpreted hinge of the area. So as we go towards the southeast, we look as though we're getting into a fold hinge, which is where structure should increase. So there are a number of deposits that are associated with fold hinges, Key Lake being one of my favorite ones, and we're hoping to see something better. And again, the mineralization is picking up as we go this direction, so we will continue that trend. Here's the calc-silicates basically, or this horizon. So as a fold is, everybody should hopefully know what a fold is, whether it's geological or not, but what you're seeing on one side, theoretically, you should see on the other side too. And we think this is a synform fold. So if we take this section here, what a synform is just basically a U-shape. So here's our section that we know of so far. If we take the U-shape and are assuming that we're going to see the same rock types on the other side, well, then there is potential for more mineralization as we go towards the east. And that really fits with our unconformity potential that we have going to the east. But I also want to notice within this magnetic survey is that you do get these breaks trending northeast and southwest. Pretty clear breaks in my honest opinion, and they look pretty large as well. When you look at the Eagle Point uranium mine, which is the largest high-grade uranium underground mine, basement-hosted underground mine in the Athabasca Basin area, you can see the controls on it. You've got your main trend, which seems to be well, in theirs is north-south. I've rotated it, but then at those cross-structure vertices, those cross-structure locations is where you get a blowout of uranium mineralization. So as we continue tracking to the southeast, we're encouraged by the idea that this will exist and that we will see these intersection points, and this is where we're going to get blowout of mineralization and hopefully higher grades, higher intercepts. So ACIO, we want to keep growing. I definitely want to keep growing this. To the east, we've shown this in the news release. Sandstone is the yellow unit on top, and on hole 5 in this area, you can see that the green unit overlies a yellow unit. So the green being the basement rocks on top of the sandstone. Well, it doesn't work. Based on the timing of events, the sandstone is younger and was deposited on top of the basement. So the only way to get basement rocks on top of the sandstone is to thrust them up on top of each other with a fault. And you see that here. So here's the unconformity potential for uranium mineralization as we track the unconformity to the east. You've got basement rocks overlying the sandstone. You get back into the sandstone rocks and they look pretty gray, I must say, which that's an alteration feature that is commonly associated with uranium mineralization. But then you go from sandstone into basement on the next interval, and that sandstone into basement is the typical unconformity. The basement to sandstone up in this area, that's a structural unconformity, and that's where everything's been thrust up. But it's that feature there that I want to focus on. Now, although we reported no elevated radioactivity for hole 5, that's not to mean there's no radiation at all. And you can see the one peak in the middle of this gamma probe survey. Also note that the scale here goes down to about 500, not 10,000. So the scale is much smaller, and zoomed in just to show everything. But we have got all the sandstone on top, and then we go into the basement rocks. And notice how the basement contact, the gamma probe is highest right at that basement contact. That's that red zone, that's that fault, because then you go back into sandstone, your radioactivity dies off, and then you go back into the basement rocks. So that fault, that red fault zone, which has the highest radioactivity along it, we think is highly prospective for uranium mineralization. We think that's a fluid conduit, and that's what we want to track. It's going to be a little bit difficult, especially with the mineralization that we have in the upper and lower zone, that trying to track the unconformity mineralization right now is not a huge priority. We want to keep drilling to the southeast. We're going to wrap up drilling to the northwest as we don't have much more room to go beyond where we are. And eventually, as we continue drilling the southeast and seeing what's down there, we will make the decision of when to explore further to the east. We do think there is a lot of potential going to the east, and we will definitely tackle it. We will look for that unconformity mineralization simply because it would be nearer to surface, higher grade typically. So it's very encouraging for us. You know, we're basically testing 3 ideas now. We're testing calc silicate mineralization at the contact with the metasediments. We're targeting that upper zone, and we've got potential for unconformity mineralization. So 3 different targets to test. Will require quite a bit of drilling to really figure it all out. So obviously, thank you for watching. Don't forget, please visit the Ore Group YouTube channel. Lots of cool videos on there from all of our peer companies and Baselode. And a big thank you from the field crews. They really appreciate everyone paying attention to Baselode, and they're hoping that you continue to watch the story as it evolves and grows. And as always, please get in contact with us via our company email, info@baselode.com. Contact myself directly, jsykes@uraniumgeologist.com. Follow us on Twitter, follow us on LinkedIn. Always happy to hear from everybody. The story is just getting started. We're on our 11th hole. We just released our 11th hole, and we've got at least 18,000 more meters to continue drilling. So we've got a big year ahead of us, and we think it's going to be fantastic as every which way goes. Thank you very much.